created by MindStick's Foundation Trust. Hello, students, and welcome to our explainer today. We're going to explore the truly fascinating life cycle of metals. I want you to pay close attention because we are going to visualize some absolutely incredible chemistry together. Here is our lesson plan for today. 1. Extracting reactive metals. 2. Moderate and less reactive. 3. The problem of corrosion. And 4. Preventing metal corrosion. Let's dive right in.
Section 1. Extracting reactive metals. The birth of aluminum.
To pull highly reactive metals out of nature, we need extreme measures, namely massive heat and electricity. Observe this setup carefully. What you're seeing is the electrolytic reduction of alumina. We take a molten mixture of alumina, and to bring its melting point down to just around 1,000 degrees Celsius, we add cryolite and fluorspar. Inside this steel tank, the inner graphite lining acts as our cathode. When we pass a strong electric current through this incredibly hot bath, the pure, heavy molten aluminum is collected right at the bottom. It's a brilliant display of using electricity to break powerful chemical bonds.
Section 2. Moderate and less reactive. The middle ground.
Now, moderately reactive metals like zinc, iron, and lead don't require that extreme electrical force, but they do require some very specific chemical preparation. The crucial point for you to understand here is the difference between these two processes. These moderate metals usually occur in nature as either sulfides or carbonates. Since it is much easier to extract a metal from its oxide, we have to convert them first. If we have a sulfide ore, we use a process called roasting, which means heating it strongly in an excess of air. But if we have a carbonate ore, we use calcination, meaning we heat it strongly in a very limited supply of air. Both of these paths lead us to a metal oxide, which is perfectly ready for the next step of reduction.
This brilliantly illustrates what happens when we use a highly reactive metal to reduce a moderately reactive one. Look at this exciting real-world application called thermit welding. Here, iron oxide reacts with aluminum powder. This reaction generates so much massive heat that the iron is actually formed in a molten state right there on the spot. This is exactly how those heavy railway tracks are welded together securely out in the field. Before we move on, we must briefly note the metals sitting at the very bottom of the reactivity series. Metals like gold, silver, and platinum are so unreactive that they don't even bother bonding with other elements. They're often found just resting quietly in nature, purely in their free state.
Section 3. The problem of corrosion. The real world takes a toll.
We spend all this energy extracting and purifying our metals, right? But what actually happens when they face the harsh realities of the outside environment? Have you ever noticed the old iron bars of a building rusting away? Or perhaps an old silver ornament turning a dull, blackish color? Why exactly do pure metals lose their shine over time? Let's uncover the chemistry of this decay.
Just look at the real-world destruction pictured here. Silver articles turn black because they react with hydrogen sulfide in the air to form a layer of silver sulfide. And consider the famous Statue of Liberty. It's actually clad in copper. Over the last 300 years, the carbon dioxide in the moist air has reacted with its surface to form a greenish layer of copper carbonate. This loss of luster, this gradual destruction, is what we call corrosion. Section 4. Preventing metal corrosion. The rescue mission.
Because metals are so incredibly useful to us, we simply cannot let them rust and decay away. We have to mount a rescue mission. The simplest method of protection is creating a basic physical barrier. By applying a layer of paint, oil, grease, or varnish to the metal's surface, we completely isolate it. If the metal can't come into direct contact with the moisture and oxygen in the air, the chemical reaction of corrosion simply cannot begin.
But paint can scratch. For much more permanent protection, we use methods like galvanizing, which you can see step by step here. In this process, iron or steel is dipped into a hot bath of molten zinc. This creates a very thin, protective layer of zinc over the iron. Because zinc is actually more electropositive than iron, it acts as a sacrifice. The zinc will corrode first, bravely protecting the inner iron from rusting away.
Another traditional and very important method is tinning, which is known locally as kalhai. Here, a layer of molten tin is deposited right onto copper or brass vessels. Now, why do we do this? Well, if you put acidic foods like buttermilk or certain curries into a bare copper vessel, a poisonous greenish layer forms and spoils the food. The tinning acts as a safe protective shield for our cooking.
Now let's look at how science uses corrosion to actually defeat corrosion. This is anodization.
Using an electrical power supply and an electrolysis bath, we purposely force a metal, like aluminum, to react with oxygen. This builds a very strong, uniform, and thick layer of aluminum oxide all over the surface, perfectly sealing the pure metal underneath from any further damage.
We can also use electricity to coat a highly reactive metal with a less reactive one. This beautiful process is called electroplating. As you can clearly see in this diagram, we are taking an everyday aluminum spoon and plating it with a very thin layer of precious silver. It protects the spoon and, of course, gives it a magnificent shine.
Finally, we have the sheer genius of alloying. An alloy is simply a homogeneous mixture of a metal with other metals or nonmetals. By mixing iron with carbon and chromium, we get stainless steel, which does not rust. By mixing copper and tin, we get bronze, which can survive the sun and rain for centuries as outdoor statues. Even the coins in your pocket are minted from various carefully crafted metal alloys to ensure they survive passing through millions of hands.
Just a brief terminology note for your exams. Whenever one of the metals in an alloy is mercury, we give it a specific name. We call it an amalgam. For instance, dentists used to use silver amalgams quite often to fill cavities in teeth.
We have covered a great deal today, from the fiery extraction of aluminum all the way to the clever chemical shields we build against rust. I'll leave you with this final thought. Look around your room, your kitchen, or your house right now. Can you identify the invisible chemical protections at work? What alloys or galvanized items are quietly protecting your home this very second? Thank you for paying such close attention to our explainer today. Keep observing and keep learning.